going to talk about the distribution of the difference between two sample means from two populations. So first I want to introduce my key. Whenever you see what looks like a mirror image of a lowercase u in English, that is a population mean. Whenever you see an X with a line over it, that is the sample mean. Whenever you see a capital N, which you don't really see much of here, that's the population size. Lowercase n is the sample size, the number that's in your sample. Sigma squared is the variance, and sigma by itself is the standard deviation. The standard deviation is the square root of the variance, as we talked about earlier. This is how you calculate the variance. The variance is you have to iterate through each value that you have in your sample or in your population. And then, so in this case, since I don't mark it here with an X with a line over it, this would probably be the population. So to find the actual variance for the population, you would take each value of X. Notice that X does not have a line over it. So this is each value that you have in the population. You take it and you subtract the average in that population from it. And then, oops, I forgot to square it. Let's use a different marker here. You square it. You have to square each one, each difference with the average. Then you divide by the number that is in the population, which is capital N there. When you do that, you get the variance. The variance is really taking into account every little deviation from the average. And it carries over, it stays what it is, because it doesn't matter whether it's greater than or less than. So you could have, this number could be greater than the average, or it could be less than the average. But since you're squaring it, it doesn't matter. So that value still carries over, and you're basically adding it up, even if it's on the lower side or the upper side of the average. So that's why variance is pretty useful. Then you take the square root of this here, and you get the standard deviation, which the standard deviation is a measure of spread of the actual curve, if it's a normal distribution. Two standard deviations is about 95% confidence interval, so about 95% of all the values that you can have are going to be within two standard deviations of the average. So if you look at these 4 standard deviations, that's about 95% of the curve. So this helps us look at the spread and how much things are varying. And I just talked about the standard deviation. When you see Z represents the number of standard deviations away from the average that a particular value is. So, and that's useful because that helps us get an idea of the probability of having a certain value by looking at the standard deviations. And you can use a table for the normal distribution for Z, and you can determine the probability of having that value, that many standard deviations away, whatever it is, from the average. And that's how you can find the probability, because we're assuming that it follows the normal distribution, and the more values that you have, and especially the higher the sample size and the more that the number in the population is, the higher that the population size is compared to the sample size, even though the sample size is at least 30 or larger, the more of a normal distribution you're going to have. The more of a normal distribution you're going to have when you have a lot of members in that population. So, like I said, if you want to look at this algebraically, you take a particular value that you have, you subtract it from the average, and you divide it by the standard deviation, and that shows you how many standard deviations away it is. That's what Z is, the number of standard deviations from the average. So I want to start out by showing an example here. I just made it up, and then, so this here is X, so that means these are individual values we're looking at. So you look at this curve, you're looking at values of X from 0 to 200, okay? And these are two different populations, so they're not identical in this case. We see that the average here is what, probably, I don't know, I would say this would be 75, that's 100, maybe 80 or something like that, close to 80. And when we look at this one's closer to like, I don't know, like 110 maybe. And then we see even that the spread is a little bit different. This one's a little bit wider, it's more distributed, which means the standard deviation is a little bit larger than this one. So we have population 1 and 2 in terms of x, each individual value. Now, so basically n equals 1. If you want to think of each value as a sample, n equals 1 here. Now let's look at it when we have a sample size of 50. And I talked about this in the last video. But as you increase the number in your sample, it starts to actually shrink the standard deviation for what you can get for an average. If we're taking the average of these, because x, the line over, is the average. So you notice that these are actually, I try to make it about 1/7 because 50 is pretty close to 49. And the square root of 49 is 7. And as we talked about in the last lecture, the standard deviation for an average, for averages from a population, is going to be the standard deviation of that population divided by the square root of n. And since we use 50, that's about 7. So basically you can take the standard deviation divided by 7 to get the standard deviation for the averages. So you see a very narrow area here. And this makes sense, as I spoke last time, according to the central limit theorem, this shrinks, you get a lot closer to 0 for the z value. And the reason for that is because values are canceling out. As you could add, say the average here is like, well, the average is what I just said. But let's say one value is 50 more and the other value is 50 less. You put those in the same set and you're averaging them, they cancel each other out. So you end up with the average. You don't even get to see that deviation in the average because they're canceling. Now, if you happen to get two 50s on one side, well, yeah, sure, that sample is going to be way over the left or way over the right, but those are extremely rare. It's likely that the number, each member that you put in there is going to be the more or less. It's just as likely to be more as it is to be less than the average. So even if you just took half of those values and you canceled out like I don't know, maybe like the standard deviation from those, you're taking away from that. And the actual equation is you take approximately, as long as the sample size is large enough, and as long as the population size is much larger than the sample size. And if it's normally distributed, the more normally distributed, the better. You end up with the standard deviation of the original population divided by the square root of n being the standard deviation for that average. And so I have that visualized here. This here is the variance of the average. Remember, it's squared, sigma squared is variance, and the subscript here is x with a line over at 1, x with a line over at 2. So red is the second population, blue is the first population. So we want to find the variance of the averages. Like I said, we take the standard deviation squared divided by n. Notice that this is just a difference of being squared or not. This is the square root of this. So this is our variance. What we want to do generally, we want to know the variability, just like we find the variance of a sample or the population. We want to keep adding the variance because we want to keep track of how many different differences we have. And since it's squared, the sign of the values does not matter. We still keep storing it as we go. Okay? The same thing is going to apply when we want to look at the difference between these two. Like we want to see what the difference between these averages is in this case. So if we want to see the distribution of the difference, we're going to want to take the variance of each of these, and we're going to want to consider that because some values are going to be a little bit higher, a little bit lower for this one, and they're going to be a little bit higher, a little bit lower for this one, and we want to find the distribution of how far away these are from each other. Now we already know that the averages are different, and I put this in green here. So this is the average, that's the average. Notice there's already a gap there. They don't have the same average in the population, okay? And that's this gap. And I show it all throughout this here, just to illustrate the concept. So if we say this difference, I don't know, I would say the difference is like almost 20, just maybe a little bit less than 20. So we already expect those averages to be about 20 apart. But, so to find out if it's statistically unlikely, we want to look at the variability that isn't contributed to by the average. So we want to actually subtract this difference. We take the average of one minus the average of the other. That gives us this green part. And notice up here, I made the sign not matter. So you're taking the average of one minus the average of the other, and it's the absolute value of this gives you this amount, positive, because negative, I don't know what negative would look like. So that's an actual scalar value, okay? Just like here, with the averages, it's still going to be the same amount because the average is still going to equal the average of the population when you do the math. And we determined that last time because all three of those have the same average. So we expect them to be at least this far apart. So if they're that far apart, that's expected. In fact, that's going to be the most common case if you were to take the averages of the differences. It's going to be most likely to be that 20 or so apart, okay? So what we want to do is we want to take the actual difference between an average of a sample from population 1, you subtract the average of the population from 2, that average of that sample. Then you want to take out what we already expect, because we don't care about that right now, we want to get rid of that. We just want to look at the actual variability between that, besides what we already expect. Just like here we subtract, like we have an individual value and we subtract the average from it, because we already expect that average to be that amount. We want to know about the extra less or more than that to find out how that compares to the standard deviation in what we're looking at. And here, we want to look at the actual standard deviation. We want to look at the difference between those and compare it to the expected standard deviation for those averages. To do that, we got to add up the variances of these two for the averages here, which I show here. These are the variances. We want to add those up because even if we're subtracting these values, we still want to add that variability because it could be more to the right and more to the right. So we would expect possibly it could still be a little bit larger. This gets a little bit less probable, and so does this. It's not as likely to be way less than this here. So what we're doing is we're subtracting out what we expect for the difference, and we're looking at just the actual difference that we wouldn't expect. Then we're dividing by the standard deviation, which is the square root of those variances added together, that actual variability that we want to know about and see if that's really, is it really probable that it's that way or not? What's the likelihood? And that's the z value, and the number of standard deviations from the expected amount of that difference. And notice, the expected amount is still that green area, that green line segment here. That's represented by 0 standard deviations. 1 standard deviation this direction and 1 standard deviation this direction it still can happen. But when you get to like 2, that's like 95% of them are going to be within these 2. If it's outside of this, we consider that significant in statistics because the actual probability of that is less than 5%. And 5% tends to be the cutoff for making tests. And when we get to 3, that's even less likely, that's lower than 0.05. 4, it's even much lower than that, like tens of thousands, or in the 10,000 order range. So, I showed you the formula for this. What we're really doing is we're looking at this variability. We're cutting out that green, and now we're just looking at how they add up. So, we could have 2 extremes. We could have this one being extremely smaller, much smaller, and this one being much larger. And in that case, we would look at these outside parts of the purple segments, which I show here. In this example, let's say they end up being like the whole width of these, but this is actually what we observe. So whatever this is, we're looking at what we actually observe here. Then in the standard deviation, we're looking at still those variances that we added up here. We're looking at whatever that is, and we're comparing this to this, and we're getting a z value. Because this would be the standard deviation, and that's whatever they actually are apart. So when we get that ratio, we get the z value, we plug the z value in using a table for the normal distribution, and we come up with a value. So let me give you an example here. So let's say we have two different samples that we pulled from different populations. We don't know if they're representative of each other, are the populations similar or not, but we do see that in sample 1, the average IQ is 130, and we took 30 of them from that. And then from a different area, a different population, we took 30 of them also, and their average IQ is 110. So given this, and also given the fact that we somehow, and I don't know how this in real life, if we already knew the standard deviation, we could probably already know the average by now. But assuming somehow we don't know the average, we just know that the standard deviation is 20 for both of them. So they could still be the same population, right? Because they have the same, at least they have the same standard deviation. If both populations are representative of each other, what is the probability of this? So if we were to pull these from that same population, we still got 130 for 30 of them and 110 for the other 30 in terms of averages. With those 30, we would actually want to basically first, let's assume they're the same population, and let's see the probability of still getting these values if they're the same population. That's a good way to test it, right? So when we do this, we want to take x1 and x2, so that would be 130, x with a line over it, by the way. That's the average, 130, average of 110. You subtract those, you get 20. Then we want to subtract the population 1 and population 2 averages. We don't actually know what the population averages are, but we're wanting to see if it's the same population. And we know if it was the same population, it'd be the same average. So we can basically make these cancel as 0 here. Then we divide that by the square root of the variances added together. Like we added the variance here and the variance there for the two samples. So since n is the same, we have the same denominator here. And since actually the population standard deviation was the same, we can square 20 for both of them. So we can basically use the same denominator, think of it as 30 in the denominator, and 400 plus 400, that's 800. So 800 divided by 30, take the square root of that, you divide that from 20, and you get 3.87. So that is our z value for this. Now, if you look at a table, you will find it'll show 0.9995 if you're looking at it as the positive value that it is, because this is greater than this one. So we'd be looking at where this red arrow is here. Now, when we look at this and we want to analyze it, we want to know what the probability is of it being the same or more extreme. So we would want to look at the probability of it being this amount or greater. We already know that 99.95% of it is already encompassed here. So that means that there's only 0.00005 on this side. So the probability of it being this extreme or even more extreme is only about 5 in 10,000. So we can just basically say, right now, these don't look like they're the same from the same population. If we randomly pick these, if this is really random of the same population, this is really unlikely. About 1 in like 2,000 that we could ever do that. So since p is much, much less than 0.05, we would conclude that these are from two different populations. They're not representative of each other. And this is an example of how we can use the math that I've built on the last lesson and this one to actually find answers to the problems. Although I would criticize it and say if we already know 20, at this point at least, in our lessons, if we already know that they're the same standard deviations for the populations, we should have already known the averages too and been able to look at that. But we're at least at this point now where we can actually make conclusions. So I hope you enjoyed this. Thank you.